Okay, well, thank you for that introduction. So my dissertation focuses on two topics. One of them is about the Hamiltonian nature of magnetic monopoles, and the other one is about the G-transform, an integral transform for kinetic plasmas. So the dissertation and also this defense will be split into those two parts. So just a brief outline first. For the Hamiltonian nature of magnetic monopoles, we'll approach this from the perspective of Vlasov-Maxwell. So we'll first look at the Hamiltonian form of Vlasov-Maxwell. Then we will add magnetic monopoles to that theory, see that it ends up not being Hamiltonian anymore. The sort of big conclusion of this section is the Jacobi identity is violated when we have magnetic monopoles. Then we'll focus down on having just one electron and one monopole, and that will help us to see more of the consequences of what happens as a result of not having the Jacobi identity. Part two is about the G-transform, which is an integral transform for kinetic plasmas. This was originally designed by Phil to solve one-dimensional linearized Vlasov-Poisson, and it gives you an exact analytic solution for that system. But you can take it and apply it to more situations. It should be able to unravel Landau damping in just about any place where it appears. So and in this dissertation, I've taken and applied it to several more situations. So what if we have collisions? What if we look at gyrokinetics or drift kinetics? And then lastly, can we use the G-transform to get non-local information from a measurement taken at one point? So, starting off with magnetic monopoles. Magnetic monopoles have never been observed. We've been looking for them for years, but many physicists still believe in them anyway. And there's two main reasons why many physicists believe in them. The first one is a symmetry argument. It makes electricity and magnetism more symmetric, and physicists love symmetry more than nature. So, of course, that's something we want. The other reason comes from Dirac was able to use the existence of a single magnetic monopole to explain why charges are quantized. So empirically, we see that electrons always have, so empirically we see that all charges have some integer multiple of the electron charge, and this will give an explanation. So the main arguments are sort of aesthetic or maybe pedagogical, but in this dissertation, I show a problem with this theory. So electromagnetism with magnetic monopoles is not a Hamiltonian theory, and that disrupts the beauty. And so we should be more skeptical. I approach this from the perspective of plasma physics, because these non-canonical Hamiltonian techniques naturally deal with particle field interactions and are automatically gauge free. But the kinetic theory I'm describing is very general, and these same conclusions result if we did a charged fluid theory or a discrete number of particles. So starting off with Vlasov-Maxwell. The key quantity for Vlasov-Maxwell is the distribution function, which tells you the probability density of finding particles of a particular species at a particular location and with a particular velocity. And the equations of motion is effectively Liouville's theorem in phase space. So we have the total derivative along a particle trajectory is constant in time, and the trajectory changes in space by velocity and in velocity by the force. You also have to couple this into Maxwell's equations to make a closed theory where the charge and current are the moments of the distribution function. So in terms of the Hamiltonian perspective, we can write this using a Hamiltonian functional and a Poisson bracket. So the Hamiltonian we're using is just kinetic energy 1/2 mv squared plus the energy in the fields. And to get the equations of motion, you need to have a non-canonical Poisson bracket then. And this bracket has several terms. We have the term that's most canonical. It has the d by dx, d by dv minus the switching them, and that gives us the basic kinematics. Then we have this term that will give us v cross b. Then we have these terms which give us the electric field in the force and also give us the current in the Ampere-Maxwell law. And lastly, we have these terms which give us the vacuum Maxwell equations. So you have E related to some curl of B and vice versa. In this expression, the subscripts are functional derivatives, and F and G are arbitrary functionals. So some basic properties of brackets. To get the equations of motion, you just take some quantity and apply and do its bracket with the Hamiltonian. So to get the Vlasov equation, you put the distribution function in here. To get the Faraday's law, you get Faraday's law and Ampere-Maxwell law, you put in E and B. Energy is automatically conserved because of the antisymmetry of the bracket. And then the divergence Maxwell equations show up as Casimirs. And so if the divergence Maxwell equations are satisfied initially, they'll be satisfied for all time. And the last thing you need to check is the Jacobi identity. And this is a property of the bracket. So you plug the bracket into itself and then cyclically permute. And it should be 0. And that's what makes the theory Hamiltonian, is it needs to have a bracket that has the Jacobi identity equal to 0. And you notice when you go through the big calculation, you get something that is not quite 0. It is proportional to div B. But that's fine because div B is 0. So we still have a valid Jacobi identity. But it does beg the question, what if div B weren't 0? And this is our first hint that magnetic monopoles might disrupt the Hamiltonian nature of electromagnetism. So typically when you see Hamiltonian electromagnetism, it isn't written in this non-canonical framework. It's instead written in terms of the potentials, phi and A. And this gives you a canonical bracket. So instead of having all the complications of the bracket, all of those terms, you instead have a simpler bracket, but a more complicated Hamiltonian. We use the non-canonical formulation, at least partially because it allows us to work completely gauge free. So we don't have to worry about how you define the vector potential when there's magnetic monopoles. That's just not an issue at all. So now we need to take this theory and add monopoles. So the way we do this is using a duality transformation. So this is a transformation this is a symmetry of Maxwell's equations. So if they're in vacuum, you can take and rotate the electric and magnetic field, basically change which one you call electric field and which one you call magnetic field, and you get the same equations of motion. But if there is matter, well, we have electric charges but no magnetic charges, so this symmetry is not there. But if we added in magnetic charges, we would then have this symmetry. And if you had all species in the system have the same ratio of electric to magnetic charge, you could just redefine what you call the electric field versus the magnetic field, and that would get rid of the magnetic charge entirely. So when we say magnetic monopoles exist, what we really say is there are some species that have electric charge and some species that have magnetic charge. If you only had magnetic charge, you could just call that field the electric field and then get rid of the monopoles that way. So the Hamiltonian we used didn't have the charge in it at all, so it stays the same. The bracket does, so we need to add 2 additional terms. So we have a term that had the electric charge and the magnetic field. Now we have one with the magnetic charge and electric field. In the equations of motion, this will give us a V cross E force. And then we also have to add in another term here that will give us a force proportional to the magnetic field, and it will also give us a magnetic current in Faraday's law. The other terms, the kinematics and the vacuum Maxwell equation terms, remain the same. And now we have to take this, show that it gives the right equations of motion, and check its Jacobi identity. So I won't show the calculation for the Jacobi identity because it takes up almost 20 pages in my dissertation. So please look at that if you're interested for the details. But when we do the calculation, we end up with this. And you might notice it's not obviously 0. Since f, g, and h are arbitrary functionals, This first part of the integral we can't force that to be 0 because it's arbitrary. So we're left with trying to figure out how to make this fs times e div b minus g div e 0. If we could make it be 0, then we can make this into a Hamiltonian theory and everything's fine. But I'll show that we can't. And the two ways we might try is, first, we might say, well, maybe this quantity, this combination of the fields is divergenceless. And so then that would make this 0. But in order to do that, we need all species to have the same ratio of electric to magnetic charge. And these aren't real monopoles. These are just, we've decided to call the magnetic field the electric field and vice versa. So this is sort of a trivial case where we can just do a duality transformation, say, oh, hey, look, we're back to electromagnetism as we see it. The other possibility is you might want to try to play some games with the distribution function and this combination. And we will discuss that further below once we look at the one electron, one monopole case. But I'll show that this is not a physical constraint either. Or this is, yeah. Okay. So if we look at one electron and one monopole, this is actually included in the Vlasov equation. We just have to pick a particular distribution function. And that is a distribution function which is 0 everywhere except at the location of the monopole or of the electron. And then we take that, we plug it into the Hamiltonian, we plug it into the bracket. Everything follows like it should. And we can then calculate the new Jacobi identity, and we get this quantity. And we might notice it is again not 0. It has this delta function of the difference between the positions. And this delta function comes because we have the distribution function, which is a delta function in one of the positions, times div b, for example, which will be also a delta function because you have a charge there. And then you integrate them and you get this delta function of the difference. So this is 0 everywhere unless the positions coincide. And then we have a singularity there. And that is where the big problems happen. So this tells us what we can do to achieve either fs equals 0 or divergence of this combination is 0. And I've summarized this as the no-touching theorem. The problems really happen when particles of two different species are at the same location. So in order to achieve this, then at every location where the electron's distribution function is non-zero, the monopole's distribution function has to be 0 there. And at every location where there are monopoles, the electron's distribution function has to be 0. And this is not a physical constraint. There's no reason physically why this can't happen. If you had a stationary magnetic monopole, it has a radial magnetic field. An electron moving directly towards it will have V cross B equals 0, so it will have no force. And the electron will go straight through the monopole without changing its trajectory at all. And if you have many other physical situations, like if there's a diffusion operator, obviously your distribution functions will smear out into each other in very short time. So we've shown that there is no physical situation in which we can have this Jacobi identity not be 0. So the Jacobi identity is non-zero if magnetic monopoles exist. And I summarize this in a little haiku. Electromagnetism with magnetic monopoles is not Hamiltonian. So why should we care? So we know the Jacobi identity isn't satisfied, but maybe that's just because this is sort of weird physics. We have different equations of motion. Maybe it doesn't matter that it's not Hamiltonian. So why is the Hamiltonian formulation of classical mechanics more attractive than just having equations of motion? So one of the main reasons is that most of what we know about classical mechanics is built on the assumption that the equations of motion are Hamiltonian. All fundamental physical theories we've seen have been Hamiltonian, and one of the main goals of science is to draw patterns from our observations, and so we shouldn't just lightly abandon this pattern we've seen that's lasted for hundreds of years through the revolutions of quantum mechanics and relativity. There's obviously some theories that have dissipation, which are not Hamiltonian, but we can explain that because they're not including all of the dynamics. There is some microscopic motion of atoms that's being neglected. But if we were to include all of the microscopic motion, they should also be Hamiltonian. So classical mechanics has a lot of geometric structure, and that allows us to, most of our theorems are proved based on that. So phase space will be, or is, a symplectic or Poisson manifold. Symplectic if there's no Casimirs, Poisson if there are, and the Poisson bracket ends up being a 2 form on that manifold. So we know that in classical mechanics, we have a Darboux theorem, which will prove that canonical coordinates exist. So even if your bracket starts out looking ridiculous, you always know that at least locally, there are some canonical coordinates that you could transfer to, and then you'd have a canonical bracket. We really want to show the opposite. We know that we don't have the Jacobi identity, so can we show that no canonical coordinates exist? And this is pretty easy to see because coordinate transformations are invertible by definition. So if our coordinate transformations preserve Jacobi identity, we don't have it, so we can't take it any coordinate transformation that will give us something that does have the Jacobi identity. So we know that for monopoles, there are no canonical coordinates. This also means we don't have a Hamilton-Jacobi equation to try to figure out what the canonical coordinates are. And Hamiltonian perturbation theory, which proceeds by doing a series of small canonical transformations, doesn't work. And so in particular, KAM theorem and all of those, the theorems of perturbation theory that we're used to, are no longer valid. The other main way we often write classical mechanics is in the Lagrangian formulation. And if we have a Lagrangian action principle, we can do a Legendre transform or Dirac constraint theory or something and turn it into a Hamiltonian with a Poisson bracket. So we can contrapose that. If we don't have a Hamiltonian and a Poisson bracket, then there is no Lagrangian action principle. So we can't derive these equations of motion from a Lagrangian, from an action, and the theorems of Lagrangian mechanics, in particular Noether's theorem, no longer apply. So we can't figure out a Noether current using the standard techniques. Another problem, along with all of the classical problems, is that when you try to write a quantum theory, there's even more problems. So your standard methods of quantization assume the Jacobi identity. Either you need an action principle or you need to write some commutation relations that match up with the bracket or whatever. You need to have a Jacobi identity to do this. So we can't write down a quantum theory of magnetic monopoles. This might surprise you because there are quantum theories that exist, going back to Dirac in 1931 and then again in expanding the theory in 1948. He wrote down a theory of electrons in the field of a point particle, or of a point monopole. And what he did was he actually included he worked using the vector potential. So he locally transformed to canonical coordinates using this vector potential, but there's a problem because the vector potential isn't defined wherever there's a monopole. So he has this string that starts at the location of a monopole and extends in an arbitrary direction. Along this string, the vector potential is undefined and the wave function must be 0. Now, this doesn't seem like too much of a constraint because the direction of the string is arbitrary, but the endpoint of the string is not arbitrary because it has to be at the location of the monopole. So Dirac's theory assumes that the electron's wave function is 0 at the monopole's location. And this is sort of a version of a no-touching theorem. wherever the monopole is at, the electron must be, or the electron cannot be there. And other quantum theories of monopoles suffer similar problems. There's fluid-like theories of monopoles. There's Schwinger's field theory that has monopoles. They all will have some sort of implicit no-touching theorem involved. So we can summarize this as the quantum no-touching theorem. So wherever the electron's wave function is 0, the monopole's wave function must be non-zero. Or wherever the electron's wave function is non-zero, the monopole's wave function must be 0 and vice versa. So this is, we can prove this by contradiction. If there's some region where both wave functions are non-zero, you can take a little loop within that. The electron's phase shift must be non-zero around that loop because there's magnetic charge there. And so there must be one point inside the loop where the phase is undefined or where the wave function is 0. And so in this region with magnetic charge, any loop has to contain a point where the electron's wave function is 0. So the whole region of magnetic charge must have the electron's wave function non-zero. And you can reverse this argument, start with any region where the electron's wave function is non-zero, and do a loop around for the magnetic monopole's wave function and get a similar thing. And this is an extremely strong result. There's no physical mechanism for keeping wave functions from overlapping. And so once again, we see when we try to introduce monopoles, we end up with non-physical constraints on what the particles can do, and it breaks the theory. Now, there is one kind of theory where this doesn't automatically, our arguments don't automatically apply. There are 't Hooft-Polyakov monopoles, which show up in grand unified theories. And where they come from is you have a larger theory that then has a long wavelength limit. So you have some symmetry breaking in a long wavelength limit, and there's a topological defect in this long wavelength limit, and that's what the monopole is this topological defect. So our argument is less relevant here because you really should be working at the level of the larger theory. So if you wanted to check if 't Hooft-Polyakov monopoles are valid theories, you should first write out the larger theory in a gauge-free formalism, prove the Jacobi identity there, then take the long wavelength limit that breaks the symmetry in a topologically non-trivial way, and then, if this limit still has a Jacobi identity, then it would be a valid theory, And it's not really clear what would happen, whether the larger theory wouldn't have Jacobi identity at all, or you might have something that the boundary terms can be important for 't Hooft-Polyakov monopoles, or there might be some singularities going on. But this is something we might do in future work. So, conclusions for this part. If we assume, or if magnetic monopoles exist, then classical electromagnetism is no longer Hamiltonian. The Jacobi identity fails whenever the locations of an electron and a monopole coincide. Since we don't have any experimental evidence for magnetic monopoles, we really believe in them for aesthetic reasons. Well, people who believe in them for aesthetic reasons. The failure of the Jacobi identity taints this beauty. So we shouldn't believe in monopoles unless we have some explanation for what's going on with the Jacobi identity. And that is part 1, and now we shift gears to part 2. So, an integral transform technique for kinetic systems. And this integral transform is called the G-transform. And it's designed to unravel Landau damping. So in plasmas, you can have Landau damping, which is a reversible transfer of energy from the waves to the continuum of velocity modes. And this is sort of surprising because you typically don't have reversible things damp. But since the waves have this discrete spectrum and the distribution function's velocity dependence has a continuous spectrum, you can have energy transfer in one way that will never return. And the simplest system with this phenomenon is Vlasov-Poisson. We can analytically solve this system using the G-transform, and then we'll take this technique and extend it to more situations with Landau damping. So the G-transform is built out of the Hilbert transform, which is a standard integral transform used a lot in signal analysis. And it's defined as follows. You have the principal value integral, and you have this 1 over u minus v. You need the principal value to deal with the singularity here. And some properties, it's linear. It's pretty obvious. If you have an analytical function, then the Hilbert transform relates its real and imaginary parts. So this other main applications of the Hilbert transform are in complex analysis, or Kramer's Kronig relation, for example, is the Hilbert transform. Its inverse is just negative itself. You have a useful identity when you start plugging combinations of things in Hilbert transforms into Hilbert transforms. A derivative of a Hilbert transform is just derivatives commute with Hilbert transforms. If you multiply by u, you can pull that out of the Hilbert transform, but you'll end up with an additional correction term. And then the adjoint of the Hilbert transform is just negative itself. So it's both its inverse and its adjoint are quite simple. And we will use the G-transform on or for Vlasov-Poisson. So once again, this is a Vlasov-like equation. So pretty similar to before, but now we just have an electric field because we're in one dimension, written in terms of the electric potential. And this electric field is determined by Poisson's equation. We will linearize about an equilibrium. Any function of velocity is an equilibrium of this equation. And then our perturbation will be Fourier transformed in space. The electric potential is 0 at equilibrium, and it doesn't depend on velocity at all. So we just have a Fourier transform in space and its time dependence. When we plug these in, we can simplify, eliminate Poisson's equation, and get the following. So omega p is the plasma frequency. This is a partial integral differential equation. It's linear, but it still looks like a bit of a mess. So the G-transform is built using the Hilbert transform, along with these epsilon r and epsilon I, which are components of the plasma dielectric function. Epsilon I is just the derivative of the equilibrium with some constants out front. Epsilon r involves its Hilbert transform. And then epsilon squared will be epsilon r squared plus epsilon I squared. In order for an integral transform to be useful, you have to be able to invert it. And its inverse is pretty simple. You just change a sign and divide by epsilon squared. And to prove that this really is the inverse, you use that convolution identity from before. So now we apply this to Vlasov-Poisson. The first term is simple. The G-transform doesn't care about time, so that just commutes. The second term, we have to deal with a velocity times the function, so that will use that identity we saw before, and we'll end up with a correction term. For the third term, this integral here doesn't depend on velocity because we've integrated it out. So the G-transform will just go, that's just a constant from the perspective of the G-transform. And then we have the G-transform acting on this equilibrium derivative. And the equilibrium derivative is proportional to epsilon I, so we can just write it out explicitly and see what that is. Now we plug everything back in, and we notice a lovely cancellation. So the correction term exactly cancels the electric field term. And that's why we want the G-transform. That's why we used it. It's to make the equations of motion much simpler by removing the electric field term. And what's left over is just advection. So we can solve that immediately, just e to the I KUT. And this is the solution in transform coordinates. We should transform back to get the total solution. So our initial conditions, G transformed, e to the I KUT, and then transform back. So we have an analytical solution. Let's go ahead and see what it looks like. So for equilibrium conditions, which are Gaussian in V, that's on the left here, we then just evaluate this analytical solution, and see what it does. So the top row here is for positive times. The bottom row is for negative times. Time is measured in 1 over kVt. It's non-dimensionalized that way. And what we can see is initially the density is sinusoidal. So we have some regions with more electrons and some regions with fewer electrons. But as time goes on, it shears and increasingly shears. So if we look at the density, which is the integral over velocity, so one of these vertical stripes, you'll notice you'll have some regions or some velocities which have more electrons than the background and some which have fewer. So this integral will decay with time. And you'll notice something similar happening as you go to negative times. And so it'll damp both for negative times and positive times. And if you were to start out with this as your initial condition, say the bottom right as your initial condition, you would start out with very little electric field or density perturbation, and then it would grow to some maximum and then damp back down again. So this solution has Landau damping. And the Landau damping doesn't show up at the level of the distribution function because it's a Hamiltonian system. Everything's, well, energy is conserved, phase space volume is conserved. You can't have something damp in a Hamiltonian system. So what does damp is the density and electric field. And the density is the integral of the distribution function over velocity. And you notice it will have some integral of something times e to the I kVt. And this is exactly in the form of the Riemann-Lebesgue lemma. And the Riemann-Lebesgue lemma says that when you integrate something against a rapidly oscillating function, that should be close to 0. And as time increases, the oscillation gets faster and faster, and so you should be closer and closer to 0. And this works as long as the function multiplying it is sufficiently smooth. And the only way that this function will not be smooth is if epsilon squared is 0, because this has a 1 over epsilon squared there, and so you might get a singularity. But as long as epsilon squared is never 0 along the real axis, this will damp, and this is guaranteed, for example, if the equilibrium is monotonic in the magnitude of V. And then the damping rate will be determined by the distance from the real axis to the closest 0 of epsilon squared. And this gives you the same damping rate as found in Landau's solution, but without having to do an inverse Laplace transform. So far, this feels sort of like a little magic trick. We wrote down some integral transform, and it just got rid of the complicated parts. So why does this work? And let's try to get some intuition for why it works. And there's a couple ways of getting intuition here. The first one is using complex functions. So epsilon r plus I epsilon I, and something similar for the distribution function, involving the Hilbert transform of the distribution function for its imaginary part. In terms of these complex functions, the G transform and its inverse look much simpler. So it's just a product of the two complex functions and then the real part of it. The second way we can get the intuition is using Van Kampen modes. So Van Kampen modes are the eigenmodes of the linearized Vlasov-Poisson. So they do not have any damping, but we do not see them in experiment because they are singular. And you can think of the G transform as a projection onto the Van Kampen modes. So you take whatever initial conditions you have, project it onto Van Kampen modes, use just the e to the it kind of solution for the eigenvalue, and then project back. The G transform was actually done looking at a Hamiltonian perspective again, and the purpose of it was to convert this system to action angle variables. And the action variable is this J here, and the angle is theta. And to get to action angle variables, you need to go through this G transform solution. Right, and in terms of action angle variables, the dynamics is even more trivial. So hopefully that makes the G transform feel less like magic now. So now let's apply it to some other situations. The first complication we can add is adding collisions. So we will add a Fokker-Planck collision operator to the right-hand side. This makes only one equilibrium still be an equilibrium. So we have to have a Maxwellian here as equilibrium. Any other function of velocity will gradually damp to a Maxwellian. If the collision frequency is small, you might think you want to treat this as a perturbation and do perturbation theory, but you'll notice that the collision frequency multiplies the highest order velocity derivative. So this is a singular perturbation. So if we do get some small velocity scales, then this term will still be important, even if nu is extremely small. And we have to get small velocity scales because we get this very rapidly oscillating function in velocity after a long time. So when the collision operator is important, it's really this first term that's important. The other terms will be smaller. So we need to G transform this. The left-hand side becomes advection like before. The right-hand side is more of a mess. And to figure out what's going on with this mess, we can try to commute the collision operator and the G transform. And to do this, you can notice that the collision operator acting on the G transform has this highest order velocity derivative. The derivatives can either act on G or on the epsilons from the product rule. If they act on the epsilons, then G will have a lower order derivative. So the dominant term will have the velocity derivative only acting on G. And so what this does is it means that we can commute the collision operator and the G transform plus some small term that only has lower order velocity derivatives. So these additional terms we'll call the shielding term, and I've written them out explicitly here, but you don't need to worry about them because they're always small, so we're going to drop them. Right, and the argument is either there are no rapid fluctuations of velocity, in which case the entire right-hand side is small for small nu, or there are, in which case this highest order velocity derivative is dominant. If we want to, we can add it in as a perturbation theory, and we can do perturbation theory without worrying about singular perturbations. So what we're left with is just this advection diffusion equation. And we can exactly solve this. So you can Fourier transform in velocity, then use method of characteristics, then Fourier transform back. For initial conditions, we'll use Gaussian in U, which is slightly different than Gaussian in V. And we have this solution. There's three terms in the exponential. The first one is e to the minus u squared, and it gradually gets wider because we just have diffusion. The time scale of this is 1 over nu, which is a long time scale, and we'll see that the distribution function has damped away before that becomes relevant. The second term is advection, so it's an e to the ikut term, which will give rise to Landau damping as we saw before. It's also multiplied by something that changes slowly, on timescale 1 over nu. And the third term is the interaction. And this is the most interesting one. You notice it goes as e to the minus t cubed, so it does decay. And we can estimate the time scale of this decay just by setting this quantity here to equal 1. Once again, the term multiplying it to the right changes as order 1 over nu, and so it's slowly. And the time scale is down here at the bottom. And it's proportional to nu to the minus 1/3. So when nu is small, this will be much faster than the time scale of just nu to the minus 1 that you'd expect from collisions. Once again, we have an analytical solution, so we can go ahead and evaluate it. It has the same initial conditions as before, so Gaussian in the velocity and then sinusoidal in x. And once again, we see that we have this shear developing. The two rows here, the top one is our analytical solution. The bottom one is a numerical solution that's done just with an implicit Euler integrator. You notice they look exactly the same. So we have confidence in the numerics as well as the analytics as a result. And you notice as we get later in time, we get more shear. The shear means there's lots of fine structure in velocity. So the diffusion becomes more and more important and it damps away. And this middle one is 1 decay time. So the amplitude should have decayed to 1 over e. This is half a decay time, and this is 1.5 decay times. So we can see that our estimate of the decay time does accurately capture how long it takes for the perturbation to decay. We can also look at when diffusion and advection, which one of those terms is dominant. And this gives us an explanation of when the collisions are important and when Landau damping, which is caused by advection, is important. So we just evaluate the solution on both of the terms, take their ratio, non-dimensionalize. This epsilon is a small parameter. We have non-dimensional time and non-dimensional velocity. And then plot this ratio. And you'll notice that collisions are dominant for small velocities and later times, and advection is dominant for larger velocities and shorter times. These next two plots are a similar thing, except instead of looking at where in phase or where in velocity space these terms are dominant, we integrate over velocity, or we L1 integrate over position and velocity, and just look at how they change in time. So this is the average of the terms for the entire distribution function at each time. And I plot this both in the original coordinates and the transform coordinates. So once you notice that the advection dominates for short times, and then once we get past 1 decay time, collisions start becoming comparable in size and eventually become larger than advection. This solution doesn't have the shielding term in it, but I went ahead and plugged in this, the solution into the shielding term just to make sure that it's always small. And we do see that it is always small, so we are justified in dropping it, at least an order of magnitude smaller than the dominant term. In the original coordinates, we see something similar, except we have one more term, which is the electric field, and that's initially dominant before decaying away. And once again, the shielding term is always at least an order of magnitude smaller than anything else. Okay, so that's for collisions, we were able to get a solution that has both Landau damping and diffusion and show when the two dominate. The next system that we can apply the G-transform to is gyrokinetics and drift kinetics, which are more complicated. As you can see, we have a highly magnetized plasma. We'll integrate over the perpendicular velocity to get a 3-space, 1 velocity, 1 time system. Just for a particular example, we'll have slab geometry There's nonlinearity in the perpendicular drifts, but nowhere else. And since we're running a little low on time, I will move through this quickly. We can once again G-transform it. There's a slight modification because we have quasi-neutrality instead of a Poisson equation. So epsilon I now has a slightly different form. There's no 1 over k squared. And this G-transform will remove the linear electric field term parallel to the magnetic field and doesn't make any of the other terms more difficult. So we now have advection, we still have our perpendicular nonlinearity, we have collisions, we have shielding, which we can drop, and the source term, well, it was a known function of velocity, so it's just some other known function of velocity. So this allows us to simplify the equations. They're not analytically solvable, but this could make gyrokinetic codes faster because you only have to G-transform at the beginning and for the final solution, not at every time step. One way of dealing with gyrokinetics is by taking moments. So integrating the distribution function, maybe multiplied times velocity. And that results in a hierarchy of fluid equations. We could do something similar either for the velocity v or for our transform velocity u. And to do that, we need to relate moments. The 0th moment is the same in both cases. The first moment is also the same. The second moment has a correction term. So we'll get an additional term proportional to the density when we try to relate the two pressures. So when we do these moments, the 0th order moment is exactly the same in u or v. The first order moment is different. In v, you'll have an Ohm's law. So if we drop all the terms that have variations in space or time. So the first 2 terms, then also this not perpendicular term. What you're left with is the current being proportional to the electric field. And that is Ohm's law. When we do the same thing in U, we no longer have the electric field. So we can't get anything like an Ohm's law when we do this. And this makes these gyrofluid equations in U, it's not really clear what our intuition should be with them. It's not clear what these variables mean. So while we can solve them, it's not as clear what they'll do. So the third situation where we can use the G-transform is when dealing with non-local information. So in most plasmas, we only measure at a few locations. In laboratory plasmas, you measure often at the edge. In space plasmas, we have the entire magnetosphere and we have a couple of satellites traveling through it, sampling the plasma. So this is obviously very under-measured. But so can we use data from one location to learn about the information from other location? And the idea is you want to take the data at one location, which often involves the full distribution function f of v, and you want to use that and follow the particles' trajectories out away from the location of the spacecraft to some other location. So to do that, we convert to a first order PDE. This is where the G-transform comes in. Then we follow these characteristic curves that sort of follow particle trajectories more or less. And that allows us to take information at one place and move it somewhere else. And then we undo the transforms we did in step 1 to figure out the distribution function elsewhere. So just as a proof of concept, I went through and did this analytically for a very simple example. So one-dimensional linearized Vlasov, quasi-neutrality instead of a Poisson equation. The equilibrium will be Lagrangian, which is not a very physical one because its energy is undefined, but it is very easy to Hilbert transform, and that's the goal of the proof of concept. And then what I'll take is a measurement at x equals 0 and assume we've measured for all times and for all velocities. So it's a boundary condition at x equals 0. And I will once again take it as Lagrangian in both velocity and time. So we have this background Lagrangian, and there's just a little pulse that comes by us at some time. And the goal is to determine the distribution function everywhere. And we can do this. You G-transform, we get an advection equation, and then the characteristics are quite simple for an advection equation. And so we can plug those in to our initial conditions, and then we G-transform back to get the exact solution. And we did this analytically, and it's a big mess, which is not written out in full because it takes an entire page of the dissertation. But you notice, so A, B, and C, and also this W6 are all polynomials in position and time. There's also W1 through W5, which are also polynomials in position and time, which are hidden inside of A, B, and C. But you can see that it still has some sort of Lorentzian-like, some peaked thing here, and then also some polynomial in velocity in the numerator as well. It's easier to just look at pictures of it than to try to figure out the expression itself. So on the left here, we have the boundary data. So this is the Lorentzian in velocity and in time. On the right, what I've plotted is what initial conditions would create this data, this measured data. And it's quite an interesting function. In particular, x equals 0, v equals 0 has a discontinuity in it. And that's not that surprising because when v equals 0, you can't transmit any information to any other locations because the particles aren't moving to carry the information. And then I also have plots of, so these are once again velocity versus time, and the colors are amplitude of the distribution function. And this is at different locations. So the top row is positive locations, the bottom row is negative locations, and you can see what the distribution, or what a measurer would see if they sat at those locations and measured distribution function as a function of time. So, conclusions for the G-transform part. Landau damping is clearest to explain using the G-transform. It gives an exact solution, so in that sense, it's similar to Landau's, but it is much more intuitive. So I encourage anyone who is teaching Landau damping to use the G-transform. When we take the G-transform and the Fokker-Planck collision operator, we see that they almost commute. And this small correction, and if we drop the small correction, we'll get an analytical solution that shows the interaction between Landau damping and collisions. In gyrokinetics, we see that gyrokinetics and drift kinetics can also be simplified by the G-transform. So maybe we can use this for faster gyrokinetic codes. And then our final application is we see that if we measure a distribution function at one location for all time, we can use this to determine the distribution function at other locations. And we want to try this out first off on a linear plasma device in an experiment, and then maybe try to use it for space plasmas. And that is future work. So to close, here is the bibliography. And I also want to acknowledge everyone who has helped me on these projects over the years. So thank you very much, and we will start questions now. Yeah, and you can raise your hand and then you will be unmuted for the question time.
Okay, you can also record your reactions by doing that. And, or as Predrag has, doing that. So are there any questions from the general audience before we go into session? People tend to be bashful on, much more bashful on Zoom than they are in an actual classroom. So I'll wait a minute here to see if anybody overcomes their bashfulness.
I'm not a physicist, but I'll ask a question. When you said at the end that there might be experimental applications of some of that, would you do those experiments, or would those be, are you hoping other people will do those experiments?
I am more hoping other people will do the experiment. I am not entirely opposed to being in a lab myself, but I typically avoid it.
Okay, cool.
Okay, well, if there are no more questions, the plan is to kill this Zoom session, and then I'll resend invitations to the committee in just a second. So thank you again, Jeffrey, and I'll put my reactions up again.
Thank you.
And thank all of you all for attending.